All right, let's get into our second video and address the next question that we have to ask. And just a reminder, counting is still hard, even if it hasn't been for us yet. All right. So in the last video, we talked about whether we were completing steps, which we multiply, or we were completing choices, which we add. In this case, our next questions that we have to address is, does order matter or not? And is repetition allowed? And we're going to address all of those things separately. We're going to first start with some things about order. So let's take these letters. We'll say T, E, X, A, and S. If I want to find all the ways I can arrange these letters into new words just being a string, they don't have to be sensical, then I can easily count this by breaking this down into steps. And I could make a tree like I did before if I wanted to. Let's actually kind of start off with a tree. So step one would be to choose the first letter. And since I'm arranging them, I can't reuse them. Once I've used them, it's gone. So think about spelling a word on a Scrabble board with these five letters. So step one, you can choose any one of these. So we have 5 choices in step one. I'm just going to write that down. We have 5 choices in step one. We already know what we're going to do. So once we use T, we now have only 4 to come out of each branch, right? For step 2. And so forth. I'm not going to make the whole tree out again. But we can see that in the second step, we have used up a letter, so we have 4 choices. And I would imagine that you would know what we would do in step 3. If we used up a different letter, we then have 3 choices left. So we start with 5, then down to 4, then 3. Once we use that up, then 2, then 1. So if I want to arrange these 5 distinct letters, I have 5 times 4 times 3 times 2 times 1 possible ways to do that. And we should recognize this as 5 factorial. So an ordering or an arrangement, so let's say this, the number of arrangements, so when you talk about an arrangement, you're thinking order, of indistinct objects. So it changes if they're not distinct, but we'll address this first. Of indistinct objects would be in factorial, like we saw above. If I had 6 letters, I would have 6 choices in the first step, then 5, then 4, then 3, then 2, then 1. So however many I have, the number of ways to arrange them is in factorial. And these arrangements, we have a special name for them, and that's called a permutation. So permutation goes with order matters. Order matters. All right. Well, sometimes we don't want to arrange all the letters. So maybe I want us to, let's come up with these letters again, T, E, X, A, and S. And I want to find, I'm only going to make 3-letter words. So I'm going to find all 3, well, I'm not going to find them, I want to count them. So let's rephrase that. So count the number of arrangements. So these are permutations of these 5 letters of these 5 distinct objects, but we're only going to look at 3 of them at a time. So we're going to say taken 3 at a time. So, for example, T, E, X. That's one of them. So we could try to list them all. That probably is going to take us too long. So instead, let's count. So let's go back to our trusty steps. In step 1, we're going to choose that first letter. And we still have 5 choices. We use them up. So second letter, we have 4 choices. We use one of those up. And so in the last step, because we only have 3 steps this time, we choose 3. So we can count them easily if we know our n and how many we're taking at a time. But sometimes we want to talk about it, if I wrote n, so if I had n distinct objects taken 3 at a time, we would say n times n minus 1 times n minus 2. If I then wanted to go a step further and say n distinct objects taken r at a time, well, then it gets kind of painful, right? Because you start multiplying down and you're like, I don't know where I'm going to stop. So we want a way to write this that is nice and concise and uses our factorial. So up above, when we did all 5 of these letters, it was 5 factorial. If I were to write this as factorial, we agree that that's 5 factorial. But I've just multiplied my correct answer with 2 times 1, which changes it. So if I just divide it back out, then, and by the way, 2 times 1 is 2 factorial, I do get what I wanted. So 5 times 4 times 3 is actually 5 factorial divided by 2 factorial. What if I wanted to do, so we're going to count, let's say, 2-letter words from these 5 distinct. Okay, so instead we'd have 5 choices, then 4. We have to stop at step 2. And again, I'm like, well, that's not quite 5 factorial. If I put in a 3 times 2 times 1, and then divide out by a 3 times 2 times 1, what is that? That's 5 factorial on top and 3 factorial on bottom. So what does this 3 have to do with the 2-letter words? Well, it's the stuff left over after you've gone 2 steps. So if I have 5 possible steps, I could do the first 2, I should have 3 left. Similarly up here, I had 3 steps, which means to get factorial, I need 2 more steps. So if we want to write it in terms of the size of the letter, if I said 1-letter word, you would just say, oops, something has happened to my pen. I'm not sure what? Okay. Fun. So if I wanted 1-letter words, it would just be 5, right? And then we would tack on 4 factorial and divide it by 4 factorial. And what does 4 have to do with 5 and 1? It's actually, if I wanted to write it out, 5 factorial over 5 minus 4. That's what's left if I just do 1 step. 3 factorial is what's left if I do 2 steps. So what should be below 5 factorial should be 5 minus 2, because I did 2 steps and I'm left with 3 factorial. Similarly, I did 3 steps up here, so it's 5 factorial over 5 minus the 3 steps I did, factorial. And in fact, let's see if we can generalize the number of permutations, so arrangements, of indistinct objects taken r at a time is n factorial over n minus r factorial, right? We do r steps, and then what's left in the factorial is n minus r. So this is called a permutation of indistinct objects taken r at a time. We might write it as NPR, and that is the notation that we will work with many, many times in probability.